When we're thinking about whether or not a function is continuous, specifically at an x value a, we are talking about the graph here of the function. And typically the notion that we have is that you can draw the function in such a way that you don't pick up your pencil, and then this would be a continuous function. So at this value a right here, I can see that my function is continuous. However, we want a more formal definition, one that incorporates this calculus that we've learned and is something that we can check mathematically as opposed to just this notion of lifting or not lifting your pencil. And so what we want to think about is the limit. So what I can see here, right, on that graph, this is my function value, is the point that it hits on the graph there, and that is f of a. And this notion of not picking up my pencil, that f of a is exactly what I expect it to be as I come from the left and come from the right, is really saying that the limit as x goes to a of my function f of x is the same as my function value f of a. And what we have written here actually finishes the definition. So a function f is continuous at an x value a if the limit as x goes to a of f of x is equal to f of a. So let's look at an example of something that's not continuous. Suppose I had this function right here. This is not continuous at this x value a. And why is that? So here's my f of a right here. So again, I see I did have to pick up my pencil, but I want to know why, using the definition, this is not continuous. Well, here I can see that when I go follow my function from the left, and when I follow my function from the right, two different things are happening. And that tells us that the limit of this function doesn't exist. Well, if the limit doesn't exist, it certainly can't be equal to that function value. So that's one example of it not being continuous. Let's take a look at a couple other examples. So if I look at this function right here, and the closed dot right there, and that's my a. So here I can see where that closed dot is, that's my f of a. But when I trace the graph, up there is my limit. So certainly here, the limit as x goes to a of f of x, which is this L value here, is not equal to f of a. Let's take a look at another example. So if I go like this, and that's my function f of x, and here's my a value. For this function, the limit does exist, right? Right there is my L. This is going from the left, and from the right it's approaching that same y value. But there's an open hole and no closed dot at all at a. So here, f of a doesn't exist. And if my function value doesn't exist, then certainly that limit is not equal to the function value. So you need to verify that the function value exists, that the limit exists, and then that those two values are in fact equal. And that's how you can use this definition of continuity to verify whether a function is continuous or discontinuous at an x value a.